Yeah, all right. So so it's my pleasure to welcome Lyudmila Grigoryeva. She'll be talking about explainable and reliable learning of dynamic processes with reservoir computing. She'll be also talking about like advertising for a reading group on reservoir computing and dynamical systems at the end of her talk. Yeah, all right. Thank you. Thanks.
Thank you, Boumediene, for introduction. Thanks a lot to everybody who joined today's talk. And of course, I'm thankful to Boumediene and to Robert McKay for organizing this series of talks. And I hope that I will contribute also to this series of wonderful contributions which we have heard in the past months. I find this initiative extremely important, so I'm very happy to be part of it. Thank you for joining. And today's title of the talk, as we already made a couple of jokes with Joseph, is quite general. So the title does not really reflect what I will be precisely talking about. Explainable and reliable learning of dynamic processes with reservoir computing. Here, we do not talk about explainable AI, as it is a well established by now terminology in computer science and in research, but rather we will be talking about explainable and reliable learning of dynamic processes with RC systems in terms of our understanding, first of all, and trying to explain the unprecedented success of these RC systems in various learning tasks. So this, if you want, will be one of the approaches that we take in this work to try to explain why randomization in reservoir computing prescriptions plays an important role in its empirical success in learning of dynamic processes. So it is, of course, a joint work. I will make precise all the colleagues with whom this work has been done. And let me first start with the outline of today's talk. I will try to be quite brief in the beginning on the introduction. What do we mean by reservoir computing and what kind of learning tasks we're handling with these systems? How do they differ from the static learning context? And in the setting of learning dynamic processes, we will be also mentioning here a couple of universality results that have been obtained in the past, say, 2 years, 1 or 2 years that we managed, my colleagues and myself, to obtain for various families of reservoir systems. And in different settings, we will talk about that briefly, and we'll try to make a statement that these results, they are the results which we may call a weak universality results, not in the sense that these results are not deep enough or they are weak from, let's say, their mathematical statement, but rather to try to oppose that or to compare to the so-called strong universality, the definition that I will make precise in say, a few minutes. And then we will be talking about how out of traditional results, which actually provide for us the representation in terms of Volterra series expansion of analytic filters, we will be able to get an inspiration about how to construct new systems, which we call the so-called signature state defined systems. And we will show that they render the solutions which are unique and which actually coincide or represent exactly the truncated Volterra series expansion, which we use to approximate analytic filters. And in the last part of the talk, well, I'm not walking you through that because I will have to make definitions precise. And what we mean by that, we will try to put some order and to take some approach where we will try to understand what is the importance or what is the role of randomization in the context of reservoir computing systems. And that we will try to get out of the classical results of 80s, which is the so-called Johnson-Linden-Strauss lemma. And we will see how applying the reduction via the result by these two authors, we are able to obtain the reduced systems where I am announcing to you already kind of a teaser that we will try to see the importance of random state maps in reservoir systems. Okay, so there have been already quite a few talks on reservoir computing. Let me just mention something that perhaps unites all the machine learning paradigms and which is actually at the core of the interest of the special interest group, sorry for tautology, which is interested in the links or interplay between machine learning concepts with dynamical systems and what can be borrowed from both these fields in another one, and how the instruments and tools that we are having both in machine learning and dynamical systems can be used in each of these fields to understand each other better. So in general, machine learning paradigms which are created, or models if you want, which are created in order to solve the tasks in dynamic environment, they all have a common goal of reconstructing or learning an unknown target, dynamic target, out of partial, again, dynamic information. And we're talking about learning in the semi-agnostic or agnostic environment where there is very little known about the true underlying behavior of either the input-output system or a dynamical system we're trying to get some information about using the machine learning tools. So in the case of I/O systems, let me be brief, but just mention that the whole plethora of research works is mainly focused on trying to learn an I/O system out of finite observations, partially available information of input and output processes. In case of stochastic processes, we may talk about learning, for example, a Bernoulli shift out of finite number of observations. And then in the same context, we may talk about learning conditional moments of a stochastic process, which is in general not available to us, out of only a finite number of observations of its realization. And in the case when we are learning, for example, the first conditional moment, we may be talking about learning an optimal predictor in the sense of mean square error, for example. So in the context of dynamical systems, not only the concepts that we will be talking about today, meaning the reservoir computing, but also other machine learning models are used in order first, usually, to learn dynamical systems system out of its low dimensional observations. And these techniques are standard to compare with conventional methods available in the theory of dynamical systems. Well, all the way counting obviously tons of work that has been done in classical theory of DS, and the learning attractor of chaotic dynamical systems of finite observations. This is also a very active research field, and people are worried a lot about trying to put ML techniques and different paradigms in order to extract the information about the attractors. So in the situation of reservoir computing, we're looking exactly at the one of the paradigms of that type. And mathematically speaking, we're introducing a RC system as in general a nonlinear state space system, which is prescribed by these two equations that you see in front of you. So the state equation and the observation equation, which are defined by these so-called reservoir map F and the readout map H. And what this system is doing is ultimately transforming or filtering an infinite discrete time input into the output, or otherwise speaking, it's just transforming the here in the slide, you see the left and right infinite RD valued sequences into the analogous sequences just in the M with the elements in the M dimensional Euclidean space, right? So D we reserve always for the inputs, M we reserve for the outputs. Let us fix that notation. And XTs are called the reservoir states, where N is the dimensionality of the state space. Usually it is customary to work with a state space which is much larger dimensional than, say, the spaces where the elements of the input and output sequences live in. Okay, so having said this, what are the defining features which distinguish, say, this general nonlinear state space system from, let's say, classical ones, which are the systems of a type 1, 2, which we call indeed reservoir computers. And these defining features are as follows. Here you have the two schematics, which roughly speaking show to us a standard schematic representation of a reservoir computing system on the left, and one of its, say, evaluations at T on the right, where we can see that the inputs Z's are transformed into the outputs Y's, and then we have this reservoir map F and the readout H, which we just saw in the previous slide. So what is important? The first defining feature, if one tries to say which nonlinear systems we may call, or we can, let's say, relate to reservoir computing systems, these are the systems of a type which are reminiscent to a working regime or operating regime of recurrent neural networks. And here, well, for example, this kind of schematics shows you exactly that case with the condition that the reservoir map has to be randomly generated. It's often chosen sparse and fixed for the whole modeling process. And here, if you are comparing this approach to standard RNNs, it clearly has its advantages since the reservoir map is fixed, it stays unchanged for the whole modeling process, and hence there is no need to train or estimate the inner weights which we would have in the recurrent neural network as an analog to RC. So what is also important is that it is only this readout map that is subject to training or estimation, and it's also chosen from a prescribed family of functions depending on the learning task. And preferably, we are working with affine functions. We are choosing this H, preferably ultimately linear, right? So that we can handle data intensive applications and statistical inference tools are available, let's say, in abundance, okay? So, and this is the case where we are trying to put ourselves. And what is important is that one of the particular examples of such RC systems would be eco-state networks. These are the kind of RC systems which are so popular in applications. And these come down to the representation that you see in front of you, where the reservoir map is obviously defined by an activation function, sigma, which is nothing else but just the component-wise application of some, say, squashing function. And then the three objects, A, C, and zeta, where A, C, and zeta, these are respectively a connectivity matrix, A, which is often chosen also to be sparse, C is an input matrix, as it is called, or input mask, and this zeta is an input shift. And these three objects are usually generated randomly drawn from some prescribed distribution. And as I said, connectivity matrix is often chosen to be sparse. So the state equation does not admit any changes during the modeling stage. The F is prescribed and fixed, and it is only the readout, which is given to us here as basically an affine map, right, which is given by this W and A, which are subject to training and depending on the task. So these systems are quite popular. I'm not putting here references, but these eco-state networks were put on map by Herbert Jäger and many other people in different research groups. And sorry for not mentioning them by names. However, it is a very booming field, putting these eco-state networks and studying not only theoretical properties of these kind of analog of RNNs with randomly generated connectivity matrix, but also in terms of the empirical applications. And these are exactly the eco-state networks which are put to work, for example, to learn attractors of, say, all the way from, in the Lorenz case, there are papers by Patak, group of Ott, Hunt, and other colleagues of theirs, where these kind of systems are also put to work to path continue solutions of Kuramoto-Sivashinsky equations, and there is a whole plethora of research which is related to this particular example. Obviously, RC systems are much wider class of systems, which doesn't come down just to this particular example. So what are the perspectives? And here will be presumably brief. We are looking at these systems as a nonlinear state space systems, and all the advantages of nonlinear state space systems go with RC systems. So in IO systems, we are talking about realization problem, filtering theory, links with filtering theory through internal representation with latent states, then external representation with filters. For dynamical systems, we may talk about synchronization theory of dynamical systems. We may talk about approximation or representing with these nonlinear state space systems for the case of stochastic processes, and so on and so forth. Each of these branches of research would deserve a separate talk, and that is why I'm not stopping here in detail. And I'm also sorry for that, not giving you a references literature. This has been already addressed in some of the talks we had also in this special group on MLDS. So as computational tools, what is important here is that, well, these systems admit hardware implementations. Again, here there are many research groups that are worried about that. What is at the core of this work that we will be discussing is that these systems are amenable to multitasking. What that means is that through the listening stage, usually the information about the states is collected, and then only provided a given learning task of interest, the readout maps can be tuned depending on the task itself. And that is why out of a collection of states, various learning tasks can be solved just via tuning readout maps specifically for a given task. And this multitasking is an inspiration of this talk, and will give us a hint on how we can approach universality, which we will give a name, a strong universality. So this richness of a state dynamics will provide us with the tools to solve various learning tasks, just reading out those states with different readout maps, which we will on top of that choose to be linear. And that is why these systems will be easy to implement or if you want to train. Okay, so as a learning paradigm, these are systems that we're trying to make understandable. And in that sense, we have quite some work. So here I'm listing these papers not to just give you a list of what we've done, but mainly to mention all people that are working on these research questions. And here, of course, I mentioned Juan Pablo Ortega, who was also giving the talk in the special interest group on MLDS some time ago. Then, of course, I need to bring up Lucas Gonou, with whom we also have quite a few papers on generalization approximation errors for RC. And let me bring up here a paper which is at the core and the focus of this research talk, which is a joint work with Krista Cuquiero, with Lucas Gonou, myself, Juan Pablo Ortega, and Josef Teichmann. I hope that Josef is still here and didn't leave us for his seminar. And this paper is called Discrete Time Signatures and Randomness in Reservoir Computing. So what are the ingredients that we need in order to talk about universality of RC systems in various contexts? So we need a couple of features. One of them is the so-called eco-state property, and another one that we will need will be the fading memory property. The eco-state property comes down basically to the fact that we are interested in the systems, state space systems, which determine input-output systems, which happens exactly at the presence of this ESP. And we will distinguish usually two types of ESP. We will be distinguishing the ESP at the level of the system. That means that for any left infinite input sequence, taking values in some subset of d-dimensional, say, Euclidean space, there will exist a unique output sequence of an analogous structure taking with the elements in Rm, such that both the state and the observation equations hold, which I showed you before in this nonlinear state space general representation. And in that case, we can define a state space filter, as you can see in front of you. We will denote it by this UFH, and we will call this filter associated to the reservoir and readout maps F and H respectively. So these will be linked by one via the ESP. ESP at the level of the state equation will have to do just with the properties of a filter, which is associated to the reservoir map exclusively without the readout map. And obviously we can get the one that is associated to the whole system as just a composition of a readout with a filter which is associated to the reservoir map. Okay, so filters and filters are causal and time invariant. Here, I'm not stopping on that in detail. All that you need to remember is that this causality and time invariance is a very reasonable assumption about filters as objects. And it actually tells you that if you are treating the two inputs, which are indistinguishable up to some t, then the filter values will be also indistinguishable at t. And then the time invariance means that, well, your filters, they commute with the time delay operator, which comes down to just right shifting your sequence in time. Okay, very good. So the fading memory is just the encoding of the continuity property, if you want, and these will be the two basic properties that we will need for what is coming. So ESP and FMP are the two basic properties that we will need for everything that you will see in this talk. And for FMP, the only thing that we need to be careful is one has to keep in mind that in that case, we're defining filters which take values in some, well, time invariant subsets of some sequence space, which is a weighted sequence space. So it is equipped with some weighted norms, weighted norm, which is constructed for some weighting sequence, which is a decreasing sequence with a limit at 0, with a 0 element 1. And in that case, we can encode this FMP as a continuity property with respect to basically topologies which are induced by these weighted norms in the corresponding spaces, the target and the domain. Okay, so having said this, there will be many things that we will be able to avoid, technically speaking, when we will be working with uniformly bounded inputs. So the whole talk takes place in the uniformly bounded situations for the inputs. And let us just keep in mind that the only piece of notation that we will have to drag during the whole talk will be this KM. And our inputs will live in this KM, which is ultimately a subset of left infinite sequence of RD-valued elements, and we require that all the elements of these sequences will be bounded in Euclidean norm by some positive m, which is given, okay? So this Km will be the one that will prescribe for us usually the domains of our filters, so inputs will be living there. And then one more piece of notation we need, that also we will use this BM tilde in some of the statements that I will show you further. So we will also require that these inputs will be bounded in L1 sense. Okay, so there are some advantages that go with that. That's not very difficult to imagine that, well, for example, the compactness will be given to us by working with these weighted sequence spaces and working with uniformly bounded families of sequences, right? Okay, so what are the universality results available so far, which we managed to obtain in a series of works? And for uniformly bounded inputs, we have these two categories of results. One, which happens to be in the category of fading memory filters, exactly the filters that satisfy this analog of a continuity property, if you want, that I just spelled out. And the second one, without imposing FMP. We will be working mainly in the category of causal time invariant fading memory filters, and also our work, which is coming, will be also taking place for filters which have this FMP, which are FMP or have this fading memory property. So what are the approaches that we followed usually in obtaining these universality results? We took either the path where we were proving the density of relevant families, reservoir computing families, or families of RC systems with respect to the topology induced by the norm in the corresponding spaces. So if you want, we were taking the Stone-Weierstrass approach, or we were taking the approach which had to do with the internal approximation and transfer theorems, where the first approach would not work, would not be valid anymore, which is the case, for example, in some situations for eco-state networks, which, well, is the paper that I just listed in the previous slides. Okay, what are the families that were considered so far? The hero for today will be the so-called state-defined systems with linear readouts, even though following these two approaches, we managed to show that all these families that you see in front of you, including the eco-state networks, are universal. Okay, so talking about these state-defined systems, let me first tell you how this first approach works. This approach via the Stone-Weierstrass theorem, for what we are taking the inspiration is the Stone-Weierstrass theorem for real-valued functions defined on compact metric spaces. And here you can immediately understand the value of working with the inputs which are defined in this KM. and with uniformly bounded sequences. And what is important here is that we take an approach where one needs to prove that functionals generate algebras, and from that we're getting all the universality statements, which I will show you in a minute in the more general form. So what we do, we construct the vector spaces out of these filters and the associated functionals, which are defined on KM, and which these vector spaces are constituted by filters and respectively functionals which have this FMP property, so which are FMP. And we make them into norm spaces, well, by introducing the following norms that you see in front of you. And for functionals, you can see that this norm will be weighting sequence independent. And hence, we're stating the following general result, which we will call in a minute the results that lead to the so-called weak universality results. So what these results tell us? They tell us that if we're working with the inputs which are defined on KM, and we are given some index set, let us forget for a minute that we're working with the outputs which are multivariate. Let us assume that our outputs take place in the sequence space with R-valued elements. And in that case, well, this other marked product, you would not need that anymore. And then this kind of formulation would be much simpler to show to you. So just keep that in mind. And we are forming here a family of functionals which are generated by the reservoir maps and readout maps. This is the object that we introduced earlier, and we require that these functionals have the properties. So they need to be continuous, and they need to be associated to the state maps which have this state connected or state associated ESP. Moreover, well, obviously we require that, as we said earlier, that we are working at these filters, these functionals have as a domain KM. Okay, very good. So now we are forming algebras which are generated by these families of these functionals. These algebras means that ultimately we are closed under the linear combinations of our functionals and under products. So product of two functionals is still a functional out of this in order to basically have the algebra structure. And then we can state the following facts, that first, these algebra generated by such functionals will consist of continuous state space functionals. And moreover, if it contains the constant functionals and separates the points in KM, then it will be dense in the space of FMP functionals defined on KM, right, with a domain which is KM. That means that the closure of this algebra, which will be exactly the space of functionals itself, or we can equivalently say that provided given a fading memory filter, H, there will exist some member of a family of filters which will be associated to some F and H, such that it will uniformly approximate a given filter to an arbitrary accuracy epsilon. So this tells us the existence statements. We will be able to find such a functional that will approximate with respect to this infinity norm, which we just introduced in the previous slide, as accurately as one desires a given FMP filter. Okay, so what are the consequences of this result? For example, we may show that the state-defined systems will be a universal family of reservoir computing systems. And let me show you how these state-defined systems work, because they will be very important for us for what is coming. So these SigSAS systems, they are systems of a type that you see in front of you, where what we have is a linear readout. This is something that we wanted to have as a defining feature for the ease of implementation and trainability of our, say, RC system as a as a machine learning model. And then we have these prescribed, fixed P and Q, which are simply polynomials with matrix coefficients. For P, these are matrices of n dimension, and then for Q, we have these rectangular matrices of n by d, where d is just a dimensionality of our elements in our input sequences. Okay, so now what we have is that whenever these P and Q And this is, I have to be mentioned that all the nonlinearity that one has in mind will be cornered in this state equation. It will be fixed by a learner, by us, for good and left unchanged during the whole modeling process as something that we required. Once we are prescribing how this P and Q look, and we need a couple of properties so that, for example, a ESP property holds for such a system, either the state related or on the level of the whole system. And for that, we require the following properties. Something that I forgot maybe to mention is that the easy sufficient condition for the ESP to hold will be to work with contracting state maps. And this is the case, obviously, for eco-state network. For example, when we are constraining the behavior of our activation function and our connectivity matrix such that a product of the top singular value of our connectivity matrix and a Lipschitz constant of our activation function is smaller than 1. That will be a sufficient condition for the ESP to hold. What will be the condition that we will see for the SAS systems? They are given here by these constants MP and MQ, where one constant has to be smaller than 1 and another one, MQ, that has to do with a second polynomial, this QZ, has to be finite. And what we have is that in this case, we will have a unique associated state filter, U associated to P and Q on the state level, which takes the inputs from Km and maps them into KL, where you can see that KL will be of the same structure as Km, which just the difference is that the L has to be prescribed by these constants MQ and MP that are provided here in these conditions for the ESP to hold. Okay, provided these conditions holds, we are constructing a SAS of this type, we can have a unique associated filter. And this is good news because we can now put it to work. What we can say is that not only this family that I showed you before will be a universal family, I can make one step further, and as a corollary of this general theorem that you saw before, I can obtain even a smaller class of SAS systems which will be universal. For example, I can take matrix coefficients for the polynomial P, taking as nilpotent matrices of the order K, and in that case still I will be able to show that such a family will generate an algebra which will be dense in the set of these continuous functionals associated to the ESP reservoir maps. Okay, very good. So now, having said this, the SAS is a great system. We need to say that sometimes this approach based on the density doesn't work, and this is the case for eco-state networks. Modulo the recent works that Juan Pablo has published with Lucas, where they provide a different proof based on other categories. So, for example, there they still work in the category of FMP filters, and you can find this in their recent paper, which I think is published this year already. Okay, you can find it on their web pages. Here I'm giving you a statement in our common paper with Juan Pablo, where we show exactly the following, that using now this time around not these density arguments, but using this internal approximation and transfer theorems, we're able to show the following, that well, if you are looking at the filter, which is, if you're working with a given causal and time invariant filter, which on top of that is assumed to be FMP, then we can construct such a eco-state network so that the associated filter to this state map and the readout map of this ESN will approximate a given FMP causal and time invariant filter in L infinity sense as accurately as you desire. So we have, and the same property holds for the functionals. So we have universal properties for eco-state networks as well. So all this to tell you that in all these statements, now let me recap, is that we always start from the following idea. I'm giving you a, say, causal time invariant fading memory filter, and you state the existence fact. You are able to say that there will exist, you can find, it is guaranteed that there will be a such filter which is associated to some RC a system from some given family, like here, for example, equal-state network or SAS, that will approximate this given by me filter as accurately as I desire in some sense. And this what we will call a weak universality. So I'm giving you a filter and you're able to guarantee that there will exist some RC system that the associated filter to which will approximate as accurately as I desire this object. So this is bad news, because this means that whenever I'm giving you a filter, you need to search for A1 that will do the job well. Can we pose question differently? Now, coming back to this idea of multitasking, where we said that since the state equation dynamics is untouched and left untouched for the whole modeling process, can we listen to the states, can we collect them, and then use the idea that now out of those states, I'm able to read out, depending on the learning problem, tuning the linear map accordingly. This leads us to the idea of the strong universality. Or said differently, can we find a reservoir system now that will do the job well enough in terms of approximating of all fading memory filters, right? So think of two different concepts and compare them. This is much stronger notion, and that is why we give it a name, a strong universality. If the state dynamics is rich enough, that means that hopefully I will be able to approximate all fading memory filters using that state space, the filter which is associated to that state equation. Okay, so we are looking for inspirations in the solutions of controlled stochastic differential equations using the signature process. And the first steps towards the strong universality will be the following. The main tool that we will be using will be Volterra series expansion. This is quite classical tool. Obviously, the only thing that we're doing here in this theorem that you see in front of you will be just rewriting a classical Volterra approximation results for the case of left infinite sequence valued inputs, okay? So here what we are doing is the following. So sorry for notation is gonna get very heavy, but I will try to deliver all the ideas so that you at least get what we're doing here, and then you may want to look into the details in the paper. So again, what we're doing, we are looking at the causal time invariant fading memory filter U, which has compact both domain and codomain. So the domain and target are Km and Kl, taking as subsets of these corresponding L infinity minus Rd or Rm sequence spaces. And now what I additionally require is that the restriction of this filter to a ball, which is centered at 0 with a radius m, with respect to the infinity norm, will be analytic as a map. And moreover, I require that this filter evaluated at the 0 sequence is a 0 sequence itself. So then what I can say that if I'm working with the inputs, which on top of that I require to be L1 norm finite, then there will exist a Volterra series representation of a type in 4, which is a classical result. Here there is nothing new apart from the fact that we extend the results a la Zontac to the case of these specific inputs well, these filters defined as you can see here. So what are the ingredients of this representation? This is a representation. This is not approximation. We have these infinite sums over here, and we have coefficients of this expansion of this filter in the monomial basis of our tensor product spaces, right? So our J order tensor spaces in Rd, okay, on Rd. So here, these coefficients, these are the maps which are given for each J, are given by the Jth order, well, said correctly, Fréchet differentials of functionals associated to a filter we are representing at 0. And moreover, we need to mention here that, well, in the standard notation, the collection of these EI up to ED will be a canonical basis now at RD. And these sequences that appear in these expansions will be sequences in L infinity RD, and which are defined as follows. If T is equal to MK for each MK, then this is simply an element in the canonical basis of RD, otherwise it is 0, okay? Moreover, what we can say, apart from representation, now if we truncate this Volterra series expansion in terms of both P and L, what we will see is that we are able now not to represent, but to approximate a given FMP causal time invariant filter by a truncated Volterra series expansion, where, keep in mind, the DL is responsible for truncating in terms of the past sequence values Z, so how many back L-legged elements of our input sequence we're taking into account when we are constructing this expansion, and the P corresponds to how many orders of the basically Fréchet differential we're taking in our expansion. So now this approximation error will be bounded above by this expression, which is not very difficult to see, that it first talks to basically L and M, which incorporate the information about the target and domain of our filter, Km and Kl. Now this talks to the behavior of our inputs in terms of their L infinity norm. And then moreover, there is this L, WLU, which we say that this is a monotonically decreasing sequence which incorporates information about the filter we're trying to approximate. And this is a sequence which behaves such that it has a limit 0. Again, this talks to this fading memory properties ultimately of a filter that we're trying to approximate. I'm not making here this more precise than that, just to keep in mind that if I'm taking now the L infinity, this will come down to the glorious Taylor series expansion, and we will see that this part will be nothing else but the remainder of a Taylor series expansion up to the order P, okay? What is also important to mention is that the coefficients, they see the filter that we're trying to approximate. Also, the WLU sees the filter that we're approximating, so the U ultimately. However, the basis elements, or these tensor products Z, M1 plus T up to MJ plus T, they do not incorporate any information about the filter that we're trying to approximate, right? So this gives an idea about this connection of multitasking, whether we can now use the fact that ultimately expansion in this basis elements, we are able to represent any fading memory filter with something which will be reminiscent to this Volterra series expansion in its truncated form. Okay, so these are actually the comments that I just mentioned. So these elements, they are U independent, that's important. So, and they only incorporate information about the inputs. And the question is, can we design now a state space system whose solutions will be exactly a truncated Volterra expansion that we see in front of us, and hence this filter will be used in order to approximate a given fading memory filter, U, and can we also quantify the approximation error that we will commit? The answer is exactly yes. We can construct a system whose solution will be exactly what we see here in this part of this truncated Volterra series expansion. And the good news is that this is a system which has been already known to us. That's a SigSAS system. Let me mention that I will show you first how we construct the system, and then we will make sure that the unique solution that under specific assumptions the system will have will be exactly these objects that we had as this truncated Volterra series expansion. And then we will keep going in order to show that this system hence will have this strong universality. So it will, on the state level, be able to generate the dynamics, which will have bear no information about the filter we're trying to approximate, and then only out of reading the information from these states, we will be able to approximate a given filter of question, right? So ultimately speaking, some elements of this expansion will bear no information, namely something that will see these people about the filter we're trying to approximate, and it's only the linear readout that we will apply to it will bear the information about a concrete U. This way, we will be able to say that we achieve strong universality. Okay, let me show you how this system looks like. So we need a couple of components. First, we're working with uniformly bounded inputs that we already mentioned. So these are, now we are working with one-dimensional inputs to ease the notation, and basically we're working just with elements of these sequences, which will take values in this closed intervals minus mm. And nothing else changes, so this km will be again present in all the results that you will see in a minute. And now we incorporate, we also introduce the space, which will be a space where our states will live. And this space will be as something which already is natural to imagine from the Volterra series expansion result, will be spaces of tensors of order L. Think of this L truncation that we had there on Rd. D talks to the dimensionality of the Euclidean space where the elements of our input input sequences are living in. And this, well, in a standard fashion, this space of tensors of L on Rd will be written as well defined as you see here. So here nothing new, just a usual definition of tensor space. The order lowering map will be one more object that we will need for that. This is a very simple object. What this object is doing, this is ultimately a map whose operator norm will be 1. That's a linear map, and what this map will be doing, it will transform the tensor space of the order L plus 1 on Rd into the same type of a space, but of a lower order, as the name of this order lowering map suggests. So it will just truncate basically one dimension from our order of our tensor space on Rd. How we defined it? Well, let me give you just a representation in the standard basis of some vector v, and we will see that the way the lower ordering map is defined, it will just kill the first e. If you see, we start from the e I2, and we're killing the first e I1. So the first one will be just killed. This is how we are just removing one of the basically product elements from our tensor product, and this way we're lowering the dimension of the tensor space where well, the image of this map is defined. Okay, very good. So this is all that we need, plus two more objects. One will be the so-called Vandermonde vector, and another one will be non-homogeneous term. So the Vandermonde vector is a vector which is defined as follows. So if you're looking at this in a minute, this z tilde that we will see in some of the derivations which will follow, and this zt hat. So let me just tell you what the zt hat is. Well, ultimately the zt tilde contains all the monomials of our elements of our inputs up to the order p. That's not very difficult to see. And then the zt hat will contain all the tensor product. How many of the elements in this tensor product we will have will be L plus 1 of this zt minus L, where L corresponds to a leg of the input whose monomials we're incorporating. So if the L is not very difficult to see, will be 0, then the zt hat will be exactly the zt tilde. If we're taking one moleque to the past, then we will have a product of the two, and so on and so forth. And the complexity of this zt hat, this Vandermonde vector, will depend on how much to the past we're aiming to remember. The components of this zt hat in the canonical basis, these will be monomials on zt up to zt minus L up to the power p. So this will be a very rich object, which we may imagine will serving exactly the goals that we are hoping for, will contain all the information ultimately about our inputs, and hopefully this we will be using in order to establish the strong universality of a system which will be defined with inputs or using these objects as zt hat and the z tilde as ingredients. Non-homogeneous term will be important for us to put a relation between a system that I will show you now with this good old SigSAS system that I showed you. And I remind you that in this SigSAS system, what we had was ultimately, well, our xt's were defined through the p zt xt minus 1 plus q zt. And this QZT was a standing alone polynomial, right, with matrix coefficients, which were rectangular matrices of n by d dimension. So this non-homogeneous term will be important for us to put a relation between the system you will see in a minute with this SigSAS state equation that we already considered and which we proved to be weak, in a weak sense, universal already. Okay, so this non-homogeneous term will be simply, well, L times the tensor product of EI. And then what is important here is that we are supposed to arbitrarily choose this index set, which will be a subset, which necessarily needs to contain 1, and it will be a subset of all naturals up to p plus 1. And it's up to us to choose it. So the fact that I will show you in a minute will be independent on how we choose this index set. Okay, and then we are constructing this non-homogeneous term. The result is coming. We are constructing now a system. Forget about the heaviness of notation. All you need to see is this expression in 7 and this map in 8. I'm proposing to you the SigSAS system, which is inspired, and it is called the signature SAS. The reason where this name is coming from is the relation to objects which appear in the relation with rough path theory and these solutions of these control these that I mentioned. For a minute, let's forget where this name is coming from. They just call such systems SigSAS systems. And what we will have here will be the following. We will define the state dynamics using a couple of objects. I'm giving you the inputs, which look like these van der Monde vectors and this non-homogeneous term that I just introduced. We are using this order lowering map, which is doing what? We are prescribing the value of a current state as a scaled with lambda, whose behavior needs to be prescribed depending on the behavior of the input. The scaled order lowering map applied to a previous step and taking the tensor product with the inputs which contain these basically monomials, right, of the inputs up to the order p, which is up to us to fix in the beginning of the modeling step. So now the state dynamics looks like very nice. So it contains all the information about the inputs. Moreover, we can say who is the map which is associated to this state dynamics. And well, obviously from the 7, we can write it as such. And this map just takes us from the product of the tensor space of L plus 1 order on R p plus 1, not very difficult to see, with R into the exactly the same tensor space of the same order, right? So with this lower ordering map, we are staying in the same space for the new coming states as a function of the previous ones. Okay, what we need to require? We can say that this will be a contraction in the state variable with a contraction constant, which is prescribed by these relations, which have to do with the behavior of this lambda and the m tilde, which remembers the m from the km where our filter, our input sequences live through this sum up to p. With these conditions put, we're able to say that this map restricted to the KL, where KL is given by these constants, not very difficult to show, will have a solution. It will be unique, and we will have an associated filter to this F SigSAS, which will be ESP and FMP, will be continuous. And moreover, we can write down the solution as what you see in front of you. It's very cumbersome expression. However, what we can notice here is that the main ingredient of this filter is this. It contains this van der Monde vector, which, as we said, in the canonical basis will have contain all the monomials up to the order p of all the well-legged, mind this, L-legged input z t tilde that we constructed, right? So these are all up to p monomials of all the elements of the input of the inputs up to the leg L. Okay, and the second term, let us in a minute forget about what this term does. it's not very difficult to see that all the monomials that already appeared here will appear here. So this is kind of a redundant information, which for what is coming will be not that important for us. And one can actually show that if you are looking at this ingredient carefully, you can imagine that this filter can be represented as a linear map acting on a van der Waals vector in such a way that it extracts or contains all the monomials which are needed in order to represent basically a filter associated to this SigSAS system. So this is an important object which we now try to put to work. And what we first need to establish that indeed such a system is a SAS system. So this is a system of a type where the state equation is like this. And let us just match. Let us match, and we will see that indeed this SigSAS with this state equation can be seen, this SigSAS can be seen as SAS with the appropriate choice of a polynomial PZT and QZT, where QZT, and that is why this non-homogeneous term was important for us, is this ZT hat 0. And we have this PZT with xt minus 1, which is nothing else but this component in this state dynamics, which, as I said, is a scaled order lowering map applied to previous state with a tensor product with a van der Waals specific vector at t. Okay, very good. So now we convinced ourselves that SigSAS is indeed SAS, so at least it has these nice weak universality properties. And moreover, what we can say is a striking fact, which is important for us for establishing the strong universality, that, remember the Volterra series expansion that we saw earlier, it turns out that whenever I am reading out with a linear map a solution of this SigSAS, so I'm applying this linear map to a filter which we just defined and which is unique, right? I'm able to say that the error that I will be committing will be exactly the same one as we had for the Volterra series expansion. In other words, we can say the following, that the truncated Volterra series expansion of any alloditic filter coincides with a unique solution of the SigSAS space system. So SigSAS gives us exactly what we had when we talked about the classical Volterra series expansion result. And now this gives us a beautiful result. Why? Because if you are looking at this for a minute, this one does not contain any information about the filter that we are approximating. So it doesn't have a dependence on U. And it is only the linear map that is applied to this U that will be responsible for how well we are matching a given filter. However, this part will be good enough for all the fading memory filters, disregarding who is the object that we're trying to approximate. And then the error behavior will be the same one that we saw before, okay? Mind something, we will be able to approximate disregarding the U, matching the W. The quality of approximation, however, will depend on a filter, right? Which is something that one would expect. So the quality definitely will depend on a object we're trying to approximate. Okay, so let us fix what we have now. We have this SigSAS system whose solutions which is a SAS, and whose unique solution happens to be the same one which is given to us, whose say composition with a linear map is the same one as the truncated Volterra series expansion, which we used in the very first, this inspiring result, where we tried to approximate our FMP filter with a truncated Volterra series expansion. So this is great news. And now what we achieved is a strong universality. So I am able to construct this U SigSAS independently on the filter. Okay. What are other, so this is basically the recap of what I just mentioned. And what is the proof comes down just to match the coefficients in the Volterra series expansion, this truncated one, with, let's say, this linear map acting on this filter. Okay, very good. What are the good news? The good news is now I collect my states from this state equation and I'm done, because now my task is only to tune the linear map W in order to match any given FMP filter. So I can listen to the states and now use them for any learning task, which has to do with approximating some filters. Bad news that come with that, the dimension of the space is enormous. You can immediately see that working with tensor spaces of the order L+1 on RP+1 is a huge space where obviously the implementation of such systems will be very difficult. So computationally speaking, using these objects, looking at the dynamics which takes place in such spaces will be computationally not very convenient. So, and the more I want to remember to the past, the larger the L I take, or the more monomials I want to keep, or orders in my ultimately Taylor series expansion or Volterra series expansion, the larger the space will be, and obviously the growth will be exponential, okay? So this gives us bad news. However, one more thing that we need to handle here is that having this strong universality, we didn't answer the key question. What about the second defining feature? We said that state equation can be in principle created randomly generated and left for good, while we didn't see that in action yet. So what is the role of the randomness, how we can see that in action, and what is the role of sparsity here? So these are the key questions that we will try to answer now. So one way to go about that would be to use our previous papers with Juan Pablo and with Lucas Gonon, where we took two different approaches. So for example, in this group of works, we tried to get this blessing of randomness and trying to explain why randomly generated state maps are successful in learning tasks. And there we went either using the tools from the statistical learning theory and using the so-called PAC bounds, the probably approximately correct bounds for learning rules, or using the approximation error bounds for recurrent neural networks, whose particular instance would be reservoir computing systems in some under some specific assumptions. However, here we're taking a different approach. We will be using the results that come to 80s by Johnson and Lindenstrauss, and which have to do with a theory of random projections. What we will be doing, we will take the system which happened to be a good enough in terms of this connection with Volterra approximation, and we will reduce it using some random projection, and we will see what is the kind of an object that we will get, and it will happen to be that this system will be, well, if you want, behaving very similar or will be the same under some specific assumptions as just simply randomly generated systems. So let us see that in action. We will achieve two goals. We will first reduce the dimension, and we will endow our system with a randomness component, right, which we didn't see yet in what we had. Okay, so I'm taking a little bit more time. I warned Boumediene that that's going to be the case. So I will, however, try to deliver just the general ideas.
No, it's okay. Take your time. No worries. You know, you are fine. Just fine. Go ahead.
Okay.
Thank you.
Okay. Very good. So we will be using this Johnson-Lindenstrauss lemma, this JL result, which tells the following. So forget what is given here on the slide. Let us think of, say, a endpoint set in some R, n-dimensional space, and think of the following result. Whenever we are taking a collection of points in that large dimensional space, for any epsilon between 0 and 1, there will exist a linear map which takes us to a new, in principle, lower dimensional space with a k that is prescribed by this relation in 12, which has to do with the accuracy that we're ultimately hunting for, and basically the dimensionality ultimately of a space we started from. And with this condition satisfied, we will observe the following fact, that the distances between the points will be epsilon approximately respected in the new lower dimensional space under this linear map F that, as we said, will exist. So this result is very strong. It tells us that there will exist a linear map that will not spoil up to the epsilon accuracy the distances in some norm between the points in the original large dimensional space when we project those points into the lower dimensional space, as long as we keep a dimension k of this target space large enough in the sense that it should satisfy these relations. So it should be 24 log n divided by this 3 epsilon squared minus 2 epsilon cubed, which is a quite famous expression for the dimension of this target space. So, okay, with this fact put in place, this is very great that there will exist a linear map like that. The good news is that this map will not only exist, but actually it can be randomly created. So it can be taken as a random matrix, taken, for example, with elements from a Gaussian distribution with a variance which is even prescribed. So whenever we're taking the elements of this F, which is taken as simply a random matrix in K by n dimension, and these elements are Gaussian distributed with mean 0 and the variance 1 divided by K, where the K is the dimension of this lower dimensional, for the tautology target space where our A is taking us to. And then we are able even to say that the probability that this, if you want, relation about the respecting epsilon accurately the distances between the points in the original space and the target space will hold with a probability which is bounded below by simply 1 divided by n, where n is simply, in this case, this is an n-point subset of some Hilbert space. In the statement that I gave you, these will be the points in my say Rn, where n is the small n, which stands for the dimension of my original space. Moreover, this map, not only that it can be randomly drawn as Gaussian, it can be also chosen sparse. So there are these recent works which tell us that we can take the elements of this map so that this 13 holds, such that, well, it can be, for example, taken as random variables which are behaving similar to Rademacher random variables, or as random variables taking one of the 3 values -1, 1, and 0 with equal probabilities. So there are these nice works that tell us what are other ways to generate these random projecting maps so that this Johnson-Lindenstrauss result holds. And moreover, we can say something about the probability of this relation to hold, okay? So reliable random projection. Okay, very good. So what we need more will be this Q norm. Here I'm not stopping on that in detail. Just keep in mind that there will be some technicalities that have to do with the fact that we need to introduce a specific type of a norm, which basically is similar to the L1, so that we can push basically the JL results forward. Just keep in mind that there will be the specific Q norm that we have defined over here, and which has to do with basically defining this norm for this Q, which we take to be this n-point subset, which we can assume to be either finite or infinite countable of this Hilbert space. We define the specific norm as you see in front of you. Okay, so why do we do that? We do that in order to see or to show that in the k-dimensional space, there are at most k orthogonal vectors. However, we will have exp of k epsilon squared almost orthogonal vectors, which tells us that we can JL reduce our system, having all these repeated monomials in our SigSAS efficiently. Okay, so what do we do here? We are now applying a, in principle, static JL lemma to our state equation, which prescribes to us the dynamics of our states, basically using the inputs which have been constructed as these Vandermonde vectors and so on. Before doing that, what we need to say is that in principle, if I'm giving you any state space system with a contracting state map, can I JL reduce it so that the properties of this state space system are preserved under this JL projection? So let us take a state map, which is a, oh, sorry. Hello? Boumediene?
Yeah, do you hear me?
Yeah, I don't know why. I think there was on Skype that someone was calling. I'm sorry for that.
Yeah, that's all right. Yeah, I thought it was my Skype.
I muted. I apologize for that. But
no, I thought it was my Skype. Oh, what's going on?
Okay, So let me continue. So we are taking a one parameter family of state maps. We require them to be contracting on the states. And let us see if we're taking JL map, which is just a standard JL map in the sense that I gave you. So this will be a randomly generated, say, matrix with Gaussian, say, elements. If we can say that whenever we're applying this random projection to our state equation prescribed by the state map, if we can preserve some properties of this state map and basically the state space system, which ultimately will have the state map in the state equation. So what we're interested in preserving first, if we're ending up again with a contracting state map, when we JL reduce in lower dimensions, if we started with the ESP, which is obviously the case because we started from contracting map, which is one of the sufficient conditions of ESP to hold. If we are in the reduced system, we'll have this ESP property also preserved. And can we say something about also the FMP, for example, preserved? And it turns out that we're able to prove these facts. And here you see this long discussion. It's not very important for what is coming. Just keep in mind that we show that when we reduce our original state map that lives in high dimensions, we're able to show that actually the properties of it will be preserved under the random projection. Okay, so moreover, we can even control how well we are doing, and there will be a couple of ways to do it. So we are able to show that if we are trying to approximate now with a JL reduced system and the filter associated to that, our original filter, we're able even to quantify explicitly the error that we will be committing. And it will have to do with the properties of the input we're handling, basically the accuracy that we were requiring in this JL lemma. And then it will have to do with the contraction constants of a map we started from. And also it will have to do with the operator norm of our JL projecting map, okay? So now we're able to say, even to quantify how well we are doing when we're trying to approximate our original living in this huge dimensional tensor space, basically system, the states, trying to approximate a filter which is associated to that state map with a JL reduced one. Okay, good news, everything is under control, we preserve properties, and this way we can state that we apply JL lemma, which is aesthetic by its construction, the way it has been proved, to a dynamic setting. So we dynamically, randomly project the system, preserving its important properties. And finally, what we can say, now if we are linearly reading out from our SigSAS, and we are reading out from our JL reduced SigSAS system, we're able also to say what is the error that we will be committing. Okay, so this is for now it. We know how to quantify these approximation errors. We show that with JL we can go to lower dimensional space where our SigSAS is easier to implement and to train. And finally, let's see what is the connection now with this randomness. So we indeed apply this JL random map, which is, as we said, in the standard JL proof, it can be taken as simply a random matrix with Gaussian distributed elements. Can we get some information now about how do these JL reduced system look like? And if we're thinking of that for a minute, we're able to show that these JL reduced SigSAS systems are actually as the same system as if we generated the coefficients in our state equation as random matrices. So the following results shows basically this idea. The only thing that we need to do here is to construct this non-homogeneous term using this specification, taking these R as a Rademacher random variables. This prescription is arbitrary in terms of this index set that you as a learner can fix arbitrary. And now everything goes through because we are generating now, we're constructing now this Vandermonde basically vectors. The non-homogeneous term can be also written down as simply an application of this CIO map, which is nothing else but constructed from this selection diagonal matrix with elements given by Well, whenever you are in II entry, then you are getting 1. Whenever you are in II with, whenever the I is in the index set, and otherwise you are taking them as 0. That's easy, that's constructive, you can do that. And finally, we're showing this result that it turns out that now these JL reduced SigSAS systems are in the limit as n0, which is defined as simply p plus 1 in power L, where L corresponds to this lag and P to this order of the monomials that we took. As n0 goes to infinity, it turns out that these JL reduced systems will be isomorphic to the family of randomly generated SAS systems. Roughly speaking, that means that I can work simply with randomly generated SAS systems with a map which is given in 24. And moreover, I'm able even to tell you that all these AI and these Bs, they will be random matrices. I will have P plus 1 of this AI, and I am able even, thanks to the results rendered by this JL lemma, because we know how we constructed this random projection, tell you even how these entries of these matrices will be distributed. Moreover, I can even obtain a reliable result specifying this delta, which will correspond to ultimately the significance, or if you want, the 1 minus delta probability with which I will guarantee that this holds. So please keep in mind this expression over here. This tells us that now my JL reduced large dimensional SigSAS systems are in the limit isomorphic with this skewed lower dimensional SigSAS with randomly generated coefficients, which I can do easily, and then I can read out with a linear map, basically tuning it to any learning task of a question. Okay. So finally, we are able also to bound the errors. This you can look in the paper. So we can show what error you will be committing, trying to approximate a starting filter, which was our starting hero of the day, this FMP, working with randomly generated SigSAS and reading them out with a linear readout map. Okay. So let me show you the numerical illustration, and here I stop. Sorry for taking slightly longer. Let me show you now a simple example of a popular GARCH process. It's popular in econometric sense, a time series modeling of financial data. But the filter which is associated to this system which you have in 30, it happens to be analytic. This is what we needed for our Volterra series expansion, and this is the assumption that we used throughout all these results. And it has a very complicated nonlinear expression, which I didn't put it in the slide, but just believe me that approximating a filter which is associated to this GARCH process, which is generated basically as a process with a time changing variance, which is given to us by this so-called GARCH equation, which is parameterized by given parameters, which, well, we are prescribing first, and we're trying to see whether we can now, with these 3 types of systems, approximate a filter associated to 30 successfully. So let us use that, and let us see the following. First, we will construct a SigSAS in this large dimensional system for different P and L, and we will see how well we are approximating the GARCH process. Now, next, we will construct now the JL reduced. So we will start with this original. We will apply to it the JL random projection. And finally, we will just construct a randomly generated SAS. And our goal is to see that these, obviously, 2 will be linked by the results that we had before. The SigSAS will be able to approximate this filter due to the approximation results that we also had available. And moreover, these people in the limit, as P plus 1 in the power L goes to infinity, they will be isomorphic, which means that they should behave similar as our P and L goes to infinity. So this is our goal. And let me show you how this looks. So this figure shows the following. I'm just seeing how I'm able to approximate my GARCH by this SigSAS with the states in this T L plus 1 on R P plus 1. Okay, this is what we have. And I'm seeing that varying the P and my N is a function p plus 1 in the power L plus 1, I'm seeing that, well, the error that I'm committing, keep in mind that all these values need to be multiplied by 10 minus 4 to get a real value. And these are the box plots which come from generating different paths of this Garch process, because it is driven by this ZT, which is normally distributed. So I'm able to generate many paths like that. Here we took 200 Garch paths, and we are able to see that the SigSAS indeed approximates well, as n goes to infinity, our original process. Next step, let us see if now they look a little bit blurred, I'm afraid. But now let us see the following. I think that I pasted the same. Here it goes. Sorry for that. And now let us see the following. Can we now JL project our original system, see how it is able to approximate our Garch process? And now, not knowing anything about the Garch process, I will simply generate randomly my coefficients in my state equation in appropriate dimensions. And I am supposed to see that if these isomorphic properties hold in the limit, I'm able to see no difference between the JL reduced original system, which contains the information ultimately about the DL and P, and the reduced one, which I just randomly generate according to this Gaussian prescription that I showed you before. And we see that, well, here you have for the 100 and 100, for example, for K, right, 100 and 100, these two in terms of their variance and median, almost indistinguishable. The same holds for 190 and so on, where we increase the K, our target space, and the systems obviously become larger and larger as in the image, right, of my random projection. And I'm seeing that if I'm just willing to show how these guys behave, there will be no way to discriminate the result of JL SigSAS, the randomly projected, the random version of SAS, which doesn't contain any information about the original space it's coming from, and the true Garch process. And we see no distinction between the two. The conclusion of this work is the following, that we are now able to understand with this approach the blessing of the randomness in our RC systems. So in SAS case, we can see them as the following fact, so that the randomly generated SAS, so with these random coefficients, which are drawn and left unchanged for the modeling process, they approximate well any sufficiently regular I/O system just by tuning a linear readout, because they are coming and they are coinciding with the error-controlled random projection of a higher dimensional Volterra series expansion of that system. So it's in the limit isomorphic to the one that is coming from this huge dimensional system with the states living in these tensor spaces of the order L plus 1, P plus 1, and as L goes and P goes to infinity, we're getting closer and closer to the Volterra series expansion representation. Okay, so I'm sorry for taking longer, and but you saw that the notation is heavy. If one could think of a diagram, we just showed that, well, we are obtaining a SigSAS which has a strong universality properties, and just by reading by linear maps the states, we're able to approximate a wide class of fading memory filters, and just by tuning a linear map, we are approximating a given one using the strong universality properties. Thank you. And sorry, Boumediene, that I took a bit longer, but hopefully those who were not patient to see, maybe will see it in the recording, and thanks a lot.
Yeah, thank you very much. Yeah, thank you. Any questions?
I think there are not so many people that stay.
Yeah, I think it was a heavy talk. So.
Yeah.
So yeah, just like maybe like a question about, I mean, the last system. I mean, can you write the expression like to make it like look like a dynamical system, or is you said like the equations are non-trivial, but how do they look really? I mean, because I don't have an intuition.
So the system of the final
yeah, that one, yeah. No, the one after the last example, right?
Yeah, I'm just scrolling, and then it. So look, the SigSAS that we're ending up is ultimately this one, right? So if I would be willing to write down the state equation, it will just tell me that the xt is equal to the sum of the z t's, right? This t's and basically all these z at t, t, and so on, right? So I'm able to write down the state equation as what you see in 27, right?
Yeah.
And moreover, what is important here is that now I can just iteratively go, taking into account this AI and these B's are just random generated matrices in appropriate dimensions, whose behavior I know, because we said that I know exactly the law according to which the entries of these two maps are, it will take some time to, the law basically with which the entries of these random matrices are distributed. So this is all explicit. I know exactly how to generate those systems. So in this numerical example, what I did, well, you just generate, for example, for different, in this one, for example, for this box plot,
Yes.
the last one. It takes some time. So what we did, we took 160 instances. So I just generate many SigSAS with these randomly drawn A and B. And I'm trying to see if they behave as my JL reduced large dimensional SigSAS. And it happens to be the fact. So all these box plots, they tell you that the variance even is very small. And then in median, they behave similar. So there is no need to basically go from the large dimensional system via reducing it. You can already in the lower dimensional space just randomly generate your system and you will get the same performance. This in part explains why reservoir computing systems with random feature maps, something that we discussed some time ago, they perform so well because they are in the limit isomorphic to basically something which is coming from the large dimensional, huge dimensional space by just reducing it, right? So it contains all the information needed. So this in part explains with this JL approach, how come that the randomly generated state space systems, in particular SAS, they are so powerful in approximating FMP filters.
Yeah, and this, I mean, you mentioned, okay, there's a question actually. Yeah, you can unmute yourself, Rahul Sundar.
Yeah, hello.
Hello.
Thanks for the wonderful talk on reservoir computing and its usages.
Thank you.
And yeah, I have a very primitive question. So, we are trying to get a reduced order model, right? Based on which we are trying to forecast the future states of the system.
So,
essentially, I'm asking if we are trying to get a reduced order approximation of a large-scale dynamical system using an SAS, and then we are trying to predict the future states of the system, right, using that framework, if I'm not wrong.
Yeah, so here, what we are doing, we're just approximating at a given t, right? So we are not path continuing. This is all in sample. So all we are doing, you give me a process which lives between 0 and capital T, and I'm able to construct a system which is able to approximate this process of a type that you see here, for example, in this figure, which I just circled, right? So indeed, you are right that if I'm given a process, one can then path continue it, right? Because if a new state is a function of the previous one, I can just path continue and just run it in an autonomous regime using as an input the output of my system and feeding it back into the equation. And this way I can path continue. In this paper, we're not doing that, right? We're just talking about approximation properties. So we are not going out of sample. We are not looking at how basically good we will be with trying to path continue basically our process with such a system. But obviously enough, this behaves very similar to what we have for eco-state networks in particular, which happen to be very successful in path continuation, even in the case of chaotic dynamical systems. But this is something that is still on our desk, and this is a line of research that would be very interesting to pursue. But we can use it for prediction, indeed.
Just a follow-up question to that. Now, we are trying to project the dynamics of, you have a large-scale data, right? Like you have the process. so with which you train the network. Now we are projecting it onto a lower dimensional space of dimension k here, right? And then we are trying to mimic the process using this network. Now there are some traditional processes methods like you have Koopman analysis or dynamic mode decomposition, wherein you have the data and you shift the data by one time step and you build a correlation data correlation matrix and take the singular value decomposition of it, which is a linear method. So how does this SAS or echo-state networks compare with those kind of traditional methods? So
yeah, that's a very good one. So you see, what usually all these methods they lean on, right? They try to also dimension reduce. So you can use either the principal component analysis or any other methods which have the same purpose, right? They're trying to reduce the dynamics which takes place in the higher dimensional space to represent it in the lower dimensional one, hoping that the containment of information, in the large dimensional space is actually not significant and you can reduce it, right? So this is what all these singular value decomposition methods are based on. So here, this is ultimately the same, because what we're doing when we're applying this random projection method, we're just saying that, as I said, if in the k dimensional space, we have k orthogonal vectors, in the basically the reduced one, right? You have at most the expo of this k multiplied by the epsilon squared. So you have much less information contained in the higher dimensional space. So the idea here is that with this random projection, you're chopping off or you're discarding or you're basically canceling some of these monomials that we have all of them present in our state dynamics. And you're reading out only those that really play a role. So in some sense, this is very reminiscent in terms of the approach. The only difference is that here we're using just a random projection, while in PCA, singular value decomposition, and so on, there is a prescribed way in which you actually construct this projecting map, right? So either based on some correlation ideas, based on some moment behavior, and so on. But it has a rigidity, and that is why you have all this literature on nonlinear methods for dimensionality reduction, right? Where people try to avoid using just a correlation, because it may be that there is much more to the state dynamics than just a linear dependence, right? Here, we don't have that rigidity. We just know that if I generate the random map, now no information needed for that, I will still be good. And how good I will be, I am able even to explicitly quantify.
If you don't mind me taking a little more time, just a follow-up question to that. So since we are randomly initiating the weights of the reservoir map, and we're training only the parameters which map linearly to the output of the network. Right. So it so happens that we're going to be training only learning only the parameters which are of the linear connections.
Maybe I didn't quite understand. So what you mean is that we are generating the state map, right?
So I'll just rephrase it, ma'am, if you don't mind. I'll just rephrase it. So essentially, we are learning the linear only parameters that correspond to the linear map.
Exactly.
Right. So in that case, again, doesn't it fall back to a linear method? Like how does the nonlinearity play here?
Yeah, well, it's not necessarily that you can learn your linear map W using a solving optimization problem which hinges only on L2 criteria, right? And in that case, you are searching for a solution which corresponds to the smallest mean square error, which is ultimately a correlation, right? You can also figure out this linear map with other methods, not necessarily solving linear regression, which, by the way, we did here for this numerical example, but you can use another loss function for that. Okay, you will not have closed form solution, but who said that you cannot use not only the linear the correlation information from the states in your loss function? You can go much further. You can use Kullback-Leibler, you can use any kind of divergences, you can use any other loss functions, which even coming from the optimal transport if you want. So here you don't have any restriction. It's just that we know that we have a closed form solution. It would be great. yeah, to have it. But ultimately, it's not necessarily that you are supposed to lean only on the L2 criteria, which come down to correlation ultimately.
Thanks so much for the clarification.
Yes, and next question, Andrew Flynn, do you want to ask directly?
Hi, Lyudmila. So thank you for the very nice talk. So early on, you were talking about multitasking and say having memory within a reservoir system. So you're talking about universality. So you have a single system that can be trained to reproduce a time series or reproduce the dynamics you want. How about, have you been working towards universality in the sense of multitasking?
So you see, all that we did in this talk is closely related to multitasking. This means that what you're trying to show is that with your states behaving according to the dynamics prescribed by the SigSAS, you're able to represent, so you're obtaining the states which are good enough to represent any fading memory filter. So they don't see a filter that you are trying to approximate by no means. So they are good enough for any fading memory filter which you may have as your target. And then what you're doing, it is now only tuning the linear map that you are tuning it according to a specific learning task. So for example, I could train a part of this linear map in order to path continue. Part of this linear map I could train to, I don't know, forecast at steps 5. Part I could train for something else. So now with this richness in the states, you know that the filter associated to those states is good enough for any fading memory filter, which is a huge category. And now you're able parts of this linear map to train according to a concrete linear task. And you will know that you will be good enough for a variety of learning tasks, which corresponds to multitasking. You're solving a few at a time.
So you have a single system that can do
exactly
one job.
Exactly. So parts of this W that we have as a linear map, you can, if you want, reserve for different computational tasks. One serves, I don't know, you can even solve part of it as a static classification task if you're not interested in the truly dynamic processes handling, right? Part of it can be used to path continue, another part to say, I don't know, attractor learning and so on, right? I'm speaking vaguely. One has to be careful in order to specify that. But in principle, this is what people are doing. For example, training different Ws for various computational tasks. That's a standard thing. Here, we just try to show why it is possible to do so.
Okay, thank you.
So I see another. Manjunath, did you want to talk? Or?
Sorry, thank you for
hello.
Hello. I just wanted to add a comment to the question by Rahul. In Koopman's methodology, the nonlinear dynamics is approximated usually by linear dynamics in a different space. Whereas with ESNs, we're learning a linear map, but it doesn't necessarily mean that we are approximating the nonlinear dynamics by linear dynamics. We are only approximating a portion of that nonlinear map by a linear part, if I can say so.
Exactly. You're absolutely right. Yes.
Right. Okay. Thank you. That's all. I just wanted to make a comment.
Yes. That's very appropriate. Indeed. You're right.
Okay. Thank you. Thank you.
Quick question. I have a question about this memory fading property. Do the kind of tasks which are suited for like long short-term memory networks, like bracket matching, do they maybe not fall under this class of memory fading dynamics?
Well, you see, some of the results that we have in other papers, they are not necessarily stated in the category of fading memory filters with a fading memory property. So you can find, for example, for stochastic processes, Juan Pablo Ortega with Lucas Gonon, they have these universality results. not in the category of FMP filters, but then the criteria for universality, they are coming basically in the form of LP criteria, where LP is a norm which is taken with respect to a measure which is associated to the input that you are trying to treat, or let's say, which is connected to the filter that you are constructing. So there the results are of a different type. In principle, I would say that fading memory filters is a very wide category. So if you think of Markovian processes, if you think of finite memory processes, if you think of I don't know, any processes for which the far past, or let's say, doesn't matter as much as the recent past, I would say that this is a very wide category of filters. But obviously, you can find those that do not fit into that category. So I don't know which exactly you are mentioning here, but one can just simply check, right, if that's the case, if the FMP properties hold for that kind of a filter, to be sure.
It's like, I mean, one of the motivation for long short-term memory networks is that they can hold something in memory for indefinitely long until, as a function of state, it needs to be read out and deleted.
Yeah, well, I would argue that in the short, long-term systems, what they're trying to do is just to remember longer. So if you're thinking even about the ARP processes, right? So obviously, if you're working with the ARMA, which is an invertible process, you can represent it as AR infinity. So in principle, that's a process with infinite memory. However, you have the coefficients of your AR representation that decay, say geometrically decay, right? And that means that at some point, even though you have a infinite memory, that memory will not be any more significant for your learning task. So if the decay is there, at some point you need to forget what happened, or you will do it naturally. So unless you're working with long memory processes, right, for which it is a different situation, so something like fractionally integrated or processes of that type, where one has to be careful just because the autocovariances do not decay basically geometrically, but hyperbolically, right? In that case, you have to be careful. But in principle, short, long-term systems, they just remember longer, okay? So that's a motivation.
I mean, they don't remember like everything from the past end steps or whatever. They have a limited volume of memory that they can,
exactly, which is related. Yeah.
But they can be for indefinite number of time steps.
Yeah,
right?
You can. Well, with the reservoir state space systems, you can approximate a system with an infinite memory. So forget about the STL systems, right? Ultimately, you can do the same with the reservoir ones, just with the blessing that you don't need to train the inner connecting weights.
Okay.
Or you can join a few, right, in a parallel. You can also do that. You can do a pool of, say, eco-state networks with different dimensions of the state space, which will let them remember. Some will have only dimension a few neurons, virtual neurons, right? The capital N will be small, they will remember less. And then the others, huge dimensional, will remember longer. So you can also construct this short, long-term memory systems. Yeah.
I guess so. This is one point I was trying to make, is that it's not that the dimension of the memory is very, very large for long short-term memory networks. It's that the dimension is finite, but as a function of state, it will delete or add to this.
Of course, so this is what I mean. Also, of course.
Okay.
Exactly.
Okay. Well, thank you.
Any other questions? Just like last question, will you mention like attractor reconstruction? I mean, how do you think this could happen? Because I mean, here are like truncating, and then how would you go to the infinite?
Well, you see, I would say that you can do the same as you're doing with eco-state networks, right? So the same thing as people are doing well in the paper by Vlachas. I'm not sure that I'm properly pronouncing the last name right. and Ott and the groups that of his colleagues, right? What they're doing, they're using the equostate networks for that purpose, right?
Yeah.
So ultimately, you can also take a SigSAS with randomly generated coefficient matrices, and you can just do the same as what they're doing, right? Training the linear readout on one step ahead shifted version of an input. And then you path continue in an autonomous fashion, feeding what is coming out into basically the system back. And then trying to see if you are able to match this Lyapunov exponents, right, in the Lyapunov spectrum.
Yeah, exactly. Yeah.
Exactly.
Yeah.
And then you can also train this linear map according to your criteria, right, where you're checking whether all of them you match or you match only the first one, right? So,
yeah, exactly. That's what I had in mind. I was
exactly.
wondering if there is a way to tweak your thing and then train it using this Lyapunov exponents criterion. Yeah.
Exactly. So this is what one of the questions I answered, that you can actually not necessarily use basically L2 norm-based losses, right? When you train your readout, right? You can also do it with respect to any other, like for example, your criteria for the kernel methods that you are using.
Yeah, exactly. Yeah. So that, I mean, your stuff, I mean, would allow for this kind of things. I mean, you would train depending on your objective. Yeah.
Exactly.
Yeah. All right. Yeah, nice.
Another thing, whether it empirically will work better or worse, and you need compare to benchmarks, right? But well, we all have to suffer that.
Yeah, of course, yeah. And then for you, I mean, like your results, I mean, they are in a way criterion independent, or are they? I mean, how...
Well, here you see we'll just talk about approximation. So the estimation story we left outside the paper, right? So we don't say how we actually find those linear readout maps, right? So we don't say that, we just say that there will exist one, and then depending on how well you will be doing, you will be able to get better or worse error. But the thing is that if you're looking here at, for example, these box plots, you can see that the decay is slower than one would expect, going in an increase of a dimension of the SigSAS system. So you would expect a faster decay. And the problem is, because here we're using the linear regressions, they're ill-conditioned usually, and then you need to say either treat everybody equally, and then that is why you get such a decay, or then you need to do some additional work, right? Yeah. But this is what we were doing. Indeed, we don't talk about the estimation here. The estimation error will be there. We're talking only about the approximation error, at least that we're able to control. And then in this trade-off, the classical machine learning story, right? Trade-off between estimation and approximation, then you need to find a system for which both the estimation will be good enough and it's going to be rich enough to have these strong universal properties and to have a approximation error reasonably under control. But that's a different part of the story. Here we didn't in this paper even try it.
Yeah.
So we separate these. Otherwise, it's very difficult. Otherwise,
yeah, makes sense. Yeah. All right. Okay. Thank you very much. Yeah. Thank you. Any other questions?
Thank you. Yeah. Are there any questions more?
Just in case.
Yeah, there are less and less people. And
yeah, but I think the people who are interested are still around, and then maybe I thought that maybe the more you talk, I mean, the more you have questions, right?
Yeah, this is breaking the ice, right? It's called the more questions are coming.
Yeah, all right. Okay, thanks a lot. I mean, it's
thank you, Boumediene. And I was supposed to announce the reading group, but I will give you a separate information, and then
I think we should. Yeah, I think we should do it because I mean, a lot of people left anyway.
Exactly.
I think I just have to put it in the.
Yeah, maybe I think that's going to be better. Yeah,
I think like next week there'll be like a talk, so I can announce it in the email together with
exactly. And then maybe we agree on the date separately also with Juan Pablo and with Joseph, and this way we put things together and we make it precise.
Yeah, all right.
Okay, thanks a lot.
Okay, thanks a lot. Thank you
Yeah,
everyone.
Thank you. Bye-bye.